Okay, in problem 6, we have particle P. It's moving along the x-axis such that for any t greater than 0, its position is given by x sub p of t, which is equal to 6 minus 4 times e to the negative t. Particle Q moves along the y-axis such that for time greater than 0, its velocity is given by v sub q of t, which is equal to 1 over t squared at time t equals 1. The position of the particle Q is at 2, so y of 1 essentially. Okay, part A, find the velocity of particle P at time t. Okay, so remember the velocity is just the derivative of the position function. So all we have to do is take the derivative of this function. So we can write v, actually not v prime, just v of t. It's just the derivative of this, which will be, remember this is the exponential property with the natural, e, base e. So what you're going to do is just multiply this expression by the derivative of negative t. So it just becomes positive. So the derivative of negative t is negative 1. So this just becomes positive 4e is in negative t. That's it for that. Part B, find the acceleration a of t for particle q at time t. Then find all the values for find all the times when the speed of the particle is decreasing. So all the times where t is greater than 0. Justify your answer. So let's first find the acceleration. So acceleration is just the derivative of velocity. So we take the derivative of this. So a of t, and remember this is equal to just t to the negative 2. So we can just use power rule. So this will be negative 2 t to the negative 3. And we can express it like this, negative 2 over t cubed. Now, so the way it works is that when speed and when velocity and acceleration have opposite signs, that means it's going to be slowing down or speeding up. So in other words, we just have to look at what's going on. So the speed will be decreasing when the speed is positive, but the acceleration is negative, because that means it's moving in the positive direction, but that means the acceleration's moving in the negative direction. So acceleration's going against velocity essentially. So let's first find out what's going on with the speed of the particle. Speed is just the velocity in this case. So the velocity is always going to be positive. It looks like the velocity is always going to be positive because you take any number and you square it, and that'll give you a positive number. So velocity is always positive. So you can see velocity is always positive, and then acceleration, whenever t is positive, you're just going to have a positive number here. So acceleration is always negative. So that's right. For t greater than 0, speed is always positive, and acceleration is always negative. So they have opposite signs essentially. So that means that the particle is always slowing down. So you can say the speed of the particle is always decreasing. So it's decreasing for t is from t is 0 to infinity. or for t is greater than 0. All right, part C, find the position of the particle q at time t. Okay, so to find, the position in general, when you're given the velocity function, you're basically just going to integrate the velocity function depending on, what intervals you have. And that's going to give you, that'll basically tell you, how much it's traveled over that interval. It'll tell you its displacement. And depending on the type of function, you may have to consider the sign. But anyways, this one is rather simple actually. So the position of the particle will be the position that it started at, or the position where its position at time 1. So let's go ahead and let's write this actually. So y of q of t will be y of q of 1 plus the integral from 1, because remember we know where it is at time t equals 1, so we're going to integrate from 1 to t, and that's going to tell you how, that's going to basically tell you its displacement on this interval. So we just go ahead and we can integrate this, and we can just write, we don't have to write it out, but because we already have it here. So at time t equals 1, we're told that it's at 2 plus integral, so the velocity, so this is, remember, t to the negative 2. So to integrate this, we just do the antiderivative, so that'll be t to the negative 1 over negative 1. We're going from 1 to t. And that'll be 2 plus, so let's make sure I don't mess this up. So negative 1 over t, plugging that t in, it's just a t, minus negative 1 over the 1. I'm going to carry this over. So 2 plus, that'll be positive 1, 2 plus 1, minus t to the negative 1. So we get 3 plus, or 3 minus t to the negative 1. That's part C. All right, in part D, so as t goes to infinity, which particle will eventually be further from the origin? Give a reason for your answer. Okay, so essentially we want to see, where each particle will be, as, t, gets super large. So we want to basically want to get an idea of its position as t goes to infinity. So we're given the position function for particle p. So we simply are going to be determining the limit as t goes to infinity of this expression. So of 6 minus 4e to the negative t. And we're going to compare it to the limit of this expression, the limit as t goes to infinity. Remember, this is the position function for particle q. So 3 minus t to the negative 1. So you want to see which one is basically larger. Which one will give you a larger value, because that basically means it'll be farther from the origin. All right, so from this, you can kind of just use some intuition. So let me write this as this. If we have 6 minus 4e to minus 4 e to the t. If we're going to plug in a super large number for t, if we're going to plug in infinity into for t, this will just basically be like a 4 over a huge number, which will just be 0. And so this will be 6. So this will approach 6. Now, likewise, this will be 3 minus 1 over t. And if we're going to plug in a huge number for t, like if we're going to plug in a billion, 1 over a billion goes to 0 as well. So the limit will be 3 for this one. So then we can say that particle p will be farther from the origin as t goes to infinity. And you can say since 6 is larger than 3, I want to follow up with that. And that's all there is to it.